Welcome back. I'm going to jump ahead, at least as far as my book is concerned, to chapter 29, which is on volumes, arc lengths, and surface areas. Of course, I'm not jumping ahead as far as Math 104 is concerned. That's the topic for this week. And it's a pretty big topic. There are two aspects of volumes. Solids of revolution, which are formed by taking some curve in the plane and revolving it around some axis in the plane. And we're only going to be considering axes which are either vertical or horizontal. I'm not going to mess around with diagonal axes. Okay. Then there are some more general solids which don't look like solids of revolution, such as a pyramid. If you take a pyramid, it's not curvy enough. There's no sort of curved sides. It's not formed by revolving. And it is possible to find these volumes. The other two topics are arc lengths and surface areas. Now what I'd like to do is spend an hour and a half on volumes and half an hour on arc lengths and surface areas. That's how I'm going to try to time it. I may not succeed. In terms of the volumes, I'm going to concentrate mostly on volumes of revolution. And if I have any time, I will speak about the more general case. But if I don't have time, I'm going to skip out and do arc lengths and surface areas, and I'll leave it to you to read the section in the book. Honestly, in Math 104, it doesn't come up very often, at least in my experience, that the solid is not a revolution. So, with that in mind, I'd like to delve in. So, we're going to be talking about solids of revolution. Just to motivate what we're going to do, just want to take some function for definiteness. I'm going to take a semicircle centered at x equals, centered at 3, 0, and it has equation y equals, say, actually, let me make sure of this. I think it's 1 minus x minus 3 all squared. I know it's 1 minus x minus 3 all squared. All right. So this is the upper half of the circle, radius 1. Now, suppose that you want to integrate this, as in find the area. Let's remember what we did. We chopped it up into strips. That's the Riemann sum, and so on. And we found the area of the strips, add it all up, get the total area, and then we let the strip width go to 0 and have infinitely many strips as a result, and see what happens to the limit. In the limit, you get the actual area. Here's another way of thinking of it. The area is the integral of y dx, where y, of course, for this particular function is this, and we need to make it a definite integral, and we're going from 2 to 4. And the way I'd like you to think of that is just to focus on one strip, a generic strip. I don't have any particular strip in mind, so I'm just going to pick one. Now, what do I know about the strip? Well, it's at position x. Its width I'm going to call dx. Technically, dx doesn't really exist. We've seen it as differentials and things like that, but let's just play with it. The height of this is about y. In fact, if it is a left-hand sort of, if the height is given by the left-hand endpoint here, it is exactly y, but otherwise it's very close to y. And so this is a strip of width dx and height y. So its area is y dx. And that's exactly the quantity that appears here. So actually, the integral, the definite integral, does two things. One, it adds them all up. It takes a lot of these strips and adds them all up. And it simultaneously takes a limit as the strip width, dx, goes down to 0. It's pretty clever. That's what the Riemann sum is. Remember, it's a limit of a sum If you think back, we did it a while ago, but it's the limit of a sum. So basically then, if you can, the name of the game, at least for finding areas, is if you can find the area of one strip, which in this case is, as I say, y dx, where y is given by whatever your function is, then you can get the complete area by whacking a definite integral in front of it, and then actually doing the integral. We're going to use the same approach to find some volumes. So I want you to imagine what happens if you take this region here underneath this curve and revolve it around the x-axis. So it's going to come out of the board and then into the board and then through, well, it hits the board again and then it's going to go through the board and around the other side. So what do we get? What shape do we get if we actually do that? You get a sphere. Centered at 3, radius 1. Okay, so how might we find its volume? Well, let's check it out. Here's the circle. Let's take a generic strip once again. There's 3. There's x. It has thickness dx, height y. If we want to revolve the whole thing about the x-axis, we could just revolve each individual strip and then add them all up. By the way, what happens when you revolve a strip? Well, let's see. This little jutting thing comes out and around. You'll get a cylinder or a disc. Okay, you've got to try to visualize this little, well, here it is, the blackboard, the eraser just coming out, bang. It's going to make a cylinder. And if you add up all these cylinders, you'll get a lumpy sphere. It's not really a sphere, right? It's sort of a lumpy approximation to a sphere. But again, as the thicknesses become smaller, it becomes a better approximation to the sphere. Okay, so what we're going to do is we're going to work out the volume of one of these disks. Now, what is it? Let's just think about it. It's a disk. It looks like this. The thickness is dx, because that was the thickness of the rectangle that made it. And the height of the original rectangle now becomes the radius of the disk. So the disk has, or cylinder, has height dx. I know it doesn't look like a height. You have to tip your head on your side to think of it as a height. But in any case, it has height dx and radius y. So its volume is pi y squared dx. Pi y squared, of course, is the area of the top or the bottom, and dx is the thickness. So that's just pi r squared h in disguise. So, of course, to get the volume of the whole thing, we just whack an integral out the front. And, of course, again, we're going, x starts at 2 and goes up to 4 to cover the whole sphere. And just for definiteness, as it were, it is already a definite integral, I'll pull the pi outside. I'm going to replace y by what it is. Well, y is the square root of 1 minus x minus 3 all squared, so it's just 1 minus x minus 3 all squared dx. And that's a relatively straightforward integral. You can just expand it or you can substitute, and you hopefully get 4/3 pi, which agrees with the formula for the volume of a sphere of radius 1. Now, when I say, I've just left you some work there. Actually, I'm not going to be doing a lot of integrals. I'm going to be writing down a lot of integrals, but I'm not going to be evaluating them. You see, that's what we did for the last 3 weeks. We did a lot of evaluating integrals, and part of the reason is so that you can find things like volumes, right? If you need to be able to find integrals in order to do volumes. So I'm mostly interested in setting up the integral. Of course, when you actually do an exam problem or a homework problem, most of the time you have to solve the integral as well. But I have seen, at least in Math 104, a number of times, maybe 20% of the questions have said, find the volume, leave your answer as a definite integral, do not evaluate the integral. So I'm not going to have a lot to say. A lot of the time, I'm going to just write down the answer and say details for you. But I do want you, in your own time, if you get a chance, to actually work out the integrals. I'm not going to say a lot about how to do the integrals. There are a couple of exceptions, and in fact, one is coming up very soon, or at least I will give you some pointers because the integral may not be straightforward. Okay, so what we've just done is the so-called disk method. That's an example of the disk method. I'm going to give you a summary of that soon, but I want to show you the other technique that we have. Suppose instead, and I have set myself up to failure just by drawing the axis like that. Let's do better and give myself more room. Suppose instead I take the same semicircle and instead of revolving around the x-axis, I revolve around the y-axis. Okay, now what does it look like? Well, I had to pick this thing up, this whole area here, and I've got to bring it around, and it'll hit there, and then I've got to bring it into the board, which I cannot do, being too corporeal, and eventually I'll come back out there. So what's that going to look like? It looks like the top of a bagel, but no poppy seeds. So, basically, it's going to look something like this. My favorite bagel store just closed. It's true. Anyway, never mind that. So, it's the top half of a bagel or a donut. Torus to be, that's a T-O-R-U-S, as opposed to some make of car. So in any case, how do we find its volume? Well, we're going to do the same trick. We're going to take a individual strip, say over here. It has width dx and height y, and it's at position x. And we're just going to see what happens if you revolve that. Well, if you revolve that, you get an annulus, or an annular. Gee, somehow something is not quite parallel here. Sorry about this. It's just hard to see from such a distance. So you get some sort of annular prism, otherwise known as a shell, a cylindrical shell. It is actually, if you took a cylinder and then cut out a thin, another cylinder that's almost as thick, just leaving that thin shell. So it's a Coke can without a top or a bottom. Okay, that's enough. Now, what's its volume? We need to do the same thing here. Well, basically, this has radius x, it has height y, and the thickness is dx. So what I want you to do is imagine it's a can, right? So we're going to cut it down here. It's pretty thin. So when we unravel it, we can straighten it out into a big rectangle. It has some thickness. Now, the height of this rectangle is y, the thickness is dx, and the entire circumference of this original can has now been straightened out. I didn't draw it very straight either, but you can imagine. And the length is 2 pi x, because that is the circumference of a circle of radius x, and this is a circle of radius x. Now, you should rightly say, wait, this cannot be a perfect rectangle, because the inner one is x, whereas the outer radius is x plus dx. So really, one of these sides is 2 pi x plus 2 pi outside of x plus dx. And so it's not really a rectangular prism. But then again, this torus, or half a bagel, is not really made up of nested shells. I have a picture in the book of what it would look like if it were 5 shells. Again, it's very lumpy, but there's something that happens, something magical, if you like, limiting, calculus, whatever it is you want to think of it, as dx becomes very small. It does become very much like the torus, and similarly, this unfolded becomes very much like an actual rectangular prism. So the point is, this is a valid approximation in the limit, and there is a bit of a proof, or at least a footnote in the book, chapter 29, but this is a very good intuitive sort of way to look at it. Now, according to this, then, the volume of the shell, vol of shell, is equal to 2 pi x, that's one dimension, width times the height is y, times the thickness dx. And so the volume of the whole thing is equal to the integral from 2 to 4 in our case, because that's where x is ranging over, 2 pi x y dx. And for definiteness, I'm going to need to make my way over here. So this volume, maybe I'll just rewrite it again. So in our case, this is the integral. I'll pull the 2 pi outside. And x is equal to just x, whereas y is equal to the square root of 1 minus x minus 3 all squared dx. And so that's going to be the volume. Now, this is one of those integrals, it's not obvious to see what it should be. It's not that difficult. It's not that difficult, but there is some care that's needed. I'll show you how to start it. Suppose we let t equals x minus 3. So dt is dx. Also, we've got to change the bounds over. When x equals 2, t is 2 minus 3, which is negative 1. When x is 4, t is 4 minus 3, which is 1. So in t land, this becomes the integral from minus 1 to 1. X is t plus 3. And then this integral works out to 1 minus t squared, and dx is dt. And in order to do this integral, split it up into 2 pieces. The first piece is t 1 minus t squared dt. And the second piece is 3 times the integral of just root 1 minus t squared. And now I'm going to demonstrate some wizardry. This is clearly an odd function. Because if you plug in minus t, t squared's the same, but you just get a minus out the front. And the region is symmetric from minus 1 to 1. So actually that integral is just 0. It's a symmetric region, odd function. We've discussed this in the past, but not for it's been a while. If you don't believe me, make a simple substitution. U equals 1 minus t squared, and you will see that it's true. As for this one, you don't actually have to do the integral either, although you could by a trig substitution. This is just the area under 1 minus t squared, which is itself a semicircle of radius 1. So that integral is pi over 2. Pi r squared, but it's only a half. So actually, this is 2 pi. First integral is 0. 3 pi over 2. So the answer is 3 pi squared. And I like to say cubic units, since it's a volume. I don't really know what the units are. It's just on a graph. Okay, the question is, if you didn't notice this being a semicircle, how would you do it? And my answer would be trig substitution. We talked about it last time. You would let t equals sine theta. Try it. That will allow you, of course, to find this integral for any, that would allow you to find the definite, indefinite integral or any other definite integral. But in this particular case, you can save some time. Anyway, as I said, I'm not going to be talking too much about how to do the integrals. It's just that this one wasn't so straightforward. On the other hand, that formula up there is the general formula, apart from the 2 to 4. This is the general formula for the shell method. So let's just summarize what we've done. As I'm erasing the board, I wonder if there are any other questions. Okay, so just to go over this part of it again, here's the shell. Its radius is x, the thickness is dx, and the height is y. Okay, so now you have to cut it out and unravel it. So this picture becomes this picture. Yeah, the question is, why not take the volume of the outer minus the volume of the inner? And that's the more formal sort of way of doing it. So if you actually do that, the volume of the outer is pi y x plus dx all squared. And then you want to subtract away pi y x squared. Okay? Now I have to erase the picture because I started writing on top of it. Okay, so this is the volume of a cylinder of radius x plus dx and height y. And this is the volume of just the cylinder of radius x. Okay, so this is actually the volume of the shell. So what actually you get when you expand it, you get pi y x squared plus 2 pi y x dx plus pi y dx all squared minus pi y x squared. And then this cancels this, and you end up with the 2 pi x y dx, which is the same as what we found, plus a term with a dx squared, which is of much, much smaller magnitude than this. When you integrate the dx, at least, the dx goes away, as it were. You're adding up infinitely many things, but they're of the same sort of order of magnitude. The dx squared is much, much smaller. And you do need to justify that it goes away. But it does. And to my mind, a prettier way of seeing it is to approximate it by that. Okay? So that's a more formal justification. All right? Any other questions? Well, I'd like to summarize the two methods. As I'm erasing the board, just want you to note that this disk method, there's the formula, it doesn't involve x. It doesn't matter where the disk is. It still has the same volume. If you slide the disk around, it has the same volume. Not so with the shell. If you make the shell bigger, x changes, and it has a different volume. So x does enter into the formula for the shell method. 2 pi x y dx. All right, so I'm going to summarize the general situation, or at least the basic case. So here is the sort of standard case. What you want to do is you have some function y equals f of x, or just y, whatever you want to call it, and you have this region from a to b down to the x-axis. If you're going to rotate it, or revolve it rather, around the x-axis, then you should use the disk method. You have height y, thickness dx. So about x-axis, disk method, revolve about x-axis, disk method, and the volume is the integral from now a to b, pi y squared dx. But if you're going to revolve this around the y-axis, you get a shell. And the volume is now from integral from a to b, 2 pi x y dx. And as you look at it, I want you to understand why it is. Here you're adding up infinitely many disks with approximate volume pi y squared, because y is the radius, dx, because dx is the thickness. And here you're adding up infinitely many thin shells whose approximate volumes are 2 pi x y dx. And you can think of that, as I said, as the unfolded shell, or if you prefer, you can think of it as the difference between the outer cylinder and the inner cylinder, neglecting that really tiny term, the dx squared term. Okay? So, those are some formulas. And, you know, if you don't like the geometry of it, you could just memorize the formulas. I don't encourage it. But on the other hand, you know, if you can get the question right and have some idea of what you're doing, then that's okay. As I say, though, the best thing to do in any problem is actually to draw one of these things and be aware of what you're doing. So, if everything was just a curve under, just an area under a curve down to the x-axis and either revolved around the x-axis or the y-axis, things would be pretty simple. You would just use the formula and you would just have to be able to do integrals. You just need to know which formula to use. It's just two formulas. But life is not always that simple. And in particular, there are three variations that I can think of that make life interesting. And they're sort of real-life variations in a way, although they will appear to be a little bit contrived, I guess. So, the three variations that I have in mind of how the situation could look a little bit different, I'm going to summarize them and look at them one at a time. So, one variation is that the volume could go, or the area rather, that you're revolving could go down to the y-axis. Of course, it actually looks like it goes left to the y-axis. Well, I will say down to the y-axis, because I like turning my head on my side, and then, yes, it goes down. Okay, so in any case, that's a definite variation. If you have that sort of area, you cannot use one of these methods here. In fact, what we're going to do is cut the thing like this, so that the strips are horizontal. Anyway, more about this in a second. That's going to be one variation. Another possibility is that your area that you're revolving could look something like this. It could be between two curves. It could be between two curves. That is a different sort of problem again. Or at least it's a variation we have to be able to deal with. And the third variation is that the axis need not be the x-axis. It could be some other axis, like, say, the line y equals 2, for example. So suppose the area only goes down to y equals 2, and we're revolving about that. Or similarly, some other line parallel to the y-axis. As I said, I'm not going to deal with diagonal axes here. So these variations, as I say, make life interesting. I'm going to show you how to deal with them. And what's more, I will show you some examples of where you don't just have one of these variations, but you have maybe two of them applying, or possibly even all three. Okay, they're not exclusive. They can be layered. Luckily, there are means of taking care of all of them. So this is what I would like to show you. Right. So I don't propose to show really any examples of the basic stuff other than what I've showed you, because it is just using these formulas. It's the variations where things get tricky. Now, this is a time where I'm particularly glad these are review sessions. I've sort of really gone through the theory very quickly. I am not intending these to be the primary instruction. I'm going to show you how to solve the problems right now. Okay, so this is why these are in conjunction with the main classes. So, here goes. Variation 1. Area goes down to y-axis. So it is as in this picture that I've drawn up here. Suppose that the function looks something like this. Let's say we're interested from A to B. On the y-axis, it's, say, capital A to capital B. And the volume we want to revolve, or the area, rather, we want to revolve, lies between this curve, y equals f of x, say, and the y-axis. Well, suppose we want to revolve around the y-axis first. What is going on? Well, we take a strip, but the strip is going to be horizontal. Just think how nasty it would be if we took vertical. We probably could do it, but see, the vertical strips here are between this line, and then all of a sudden they become between this line and this curve. It's sort of two different paradigms. You could do it, you could definitely do it, but this seems a little bit easier to take your strips like this. So what does a strip look like? Well, its length is x, and now its thickness is dy. So the volume of the strip is actually x, or the area of the strip is x dy, but I really want to revolve it around the y-axis to get a disk. And so we're going to get pi x squared dy is the volume. And of course we have to add them all up, and we're going to get the integral of pi x squared dy. We don't just add them, we also let the thickness go down to 0. The question is, what are the bounds of this integral? It is a major error to write from little a to little b, whatever those numbers happen to be. It has to be from capital A to capital B in this case. See, this is an integral with respect to y. And these numbers have to be numbers on the y-axis, or whatever that variable is. Remember when we did substitution and I said, you got to watch out. If you change to t-land, you can't just change the x and the dx, you have to change the bounds. Well, it's a similar sort of thing. These numbers have to correspond to points on the y-axis, which in this case are from A to B, capital A to capital B, rather than little a to little b. All right? How about if this were shells? What do I mean? I've just said the answer to the question. Well, let me ask the question first. How about if we want to revolve this same strip around the x-axis? Well, then I'm going to use shells. Because you'll get a shell. This time the height will be x, the radius of the shell will be y, and the thickness will be dy again. This is a little piece of the y-axis. So the volume of the shell will be 2 pi y this time, x dy. And again, I've got to add up all these shells, lots of them. I can't even draw them. I did something in the book, and it took me a long, long time to draw that diagram, and I can't do it. I can't do a better job on the board. There are actually some great places online. If you search, do a search for something like, I don't know, shell method Java applet or something like that, and they show you how these things are built. I don't attempt to code anything that pretty, but I've seen them online. In any case, here you have 2 pi y x dy. Now you might think this looks very similar to the other formula that I wrote on the board above. There it is, 2 pi x y dx. Well, isn't it the same thing? You're integrating 2 pi xy. Even if I write it as yx here and xy up there. Well, it is different because this new integral down here is with respect to y, dy, and these numbers correspond to points on the y-axis as opposed to points on the x-axis. So it is important that you get this right. Now, you may notice that all we have done actually in both of these formulas, the disks and the shells, is to switch x and y. And that is not surprising. After all, if you imagine putting your head through the board on its side and looking back out. Okay, that's a pretty hard thing to imagine. But here's what the effect would be. Except that this board goes through. And, you know, if you actually had it on a transparency, that would be a really good thing to see. What you would actually see is you would see that the y-axis had become the x-axis, and the x-axis is now the y-axis, and your figure looks exactly like this except that the letters capital A and B are now on the x-axis. So I've sort of just relabeled the axes. If you're going to relabel the axes, then you're just switching the variables around. So, to me, switching x and y to handle this case, as opposed to drawing the actual disk or shell, is a perfectly legitimate way to solve the problem. You're just doing a transformation or a change of name, change of variable, switching x and y. So basically, the rule of thumb, switch x and y. Now, the main difficulty really is to know whether to use the shell method or the disk method. So even though we're in the middle of the variation 1, I want to just tell you a general sort of rule that tells you which one to use, regardless of which variation, any of these revolutions, problems, it should work. But first I need some board space. So any questions? Yeah.
On the right method, you're calculating the area underneath the function. And on the left method, you're calculating the area above the function.
I should be more precise here. Let me explain it a little bit. In this method, I'm taking this area here, and I'm revolving it around the y-axis. So in this particular case, I will get some sort of solid funnel type of shape. Right? It's like a plunger, actually. Sort of like a plunger, but solid. Okay? In this case, I was supposing that I will revolve about the x-axis. So now we take this piece and we revolve it, and we're going to get this. Well, I'm calculating its volume, but first of all, let's say what it is. It's sort of like a ring, but there's a ring. It's sort of like a ring. It's got a hole, but it's thicker, and then instead of the edge being nice, it's sort of pointy at one end, and it comes back in at the other end. So it'll look something like this. It has a hole in the middle. If I tip it up on its side, its base looks like this. I don't know what to call this. What's this? A found? Huh? Oh, a crown. Yeah, it's like a crown. It's like a crown. Good. I mean, the way I've drawn it, you'd have to have a pretty small head. But yeah, it's sort of like a crown. Good. It has this hole in the middle. So this integral finds this volume, and the other integral finds this volume. There are two different solids that you get. So if you revolve any region about the x-axis, you don't get the same region. You don't get the same solid as if you revolve around the y-axis. Okay? So I should have been more precise. Does that answer the question, basically? No worries. All right. Yeah, it's always good to just draw what you actually get on a separate picture to give yourself a sense of what the solid looks like. Even though the formulas chug along quite nicely without it. It's pretty useful. Okay, so I said I wanted to talk about when do you use the shell method and when do you use the disk method. Basically, suppose you've chopped them up into strips. So the strips could be horizontal, like this, it could be vertical. I want you to identify the thin part of the strip, and I want you to think about where the axis is. In this case, if that's the axis and this is the thin part of the thin part of the strip here is parallel to the axis. That's the disk method. And just as a reality check, in this picture over here, the thin part is vertical here, as is the axis that we were revolving around. And so this is parallel to the axis. Disk method. So what I'm saying is, if the thin part of a strip, so you've chopped it up into strips, if the thin part of a strip is parallel to the axis of revolution, use disks. But of course, if it's perpendicular, so over here, if we were revolving around the y-axis, here's the axis of revolution, there's the thin part, we're going to use the shell method. If the thin part of the strip is perpendicular to the axis of revolution, use shells. And you should be able to see it just by mentally revolving the thing, but if there's any confusion, that's a little reality check. All right, well, as an example of variation 1, suppose I take the curve y equals root x between x equals 0 and x equals 4. But I'm actually interested in this area. So that's the area. What I'd like to do is find the volume when you revolve it around the y-axis. Well, in this case, you're going to get, it's like a cone, it's like a witch's hat in a way on its top. I mean, sitting on its point. Solid. Filled in. So, well, according to my formulas, you know, if we were to take a disk like this, which is entirely reasonable, we're going to use the disk method because the thin bit is parallel to the axis. In fact, I'm just going to switch x and y. The volume is the integral of pi x squared dy. That's the disk formula with x and y switched around. I just have to be very careful that I do not go from 0 to 4. 4 is on the x-axis. I need to find this height here, which is 2, because 2 is the square root of 4, and I'm going to get the integral of pi x squared dy. Now, in order to find this integral, I actually need to know x as a function of y. You could actually do a substitution if you wanted and work out what dy was and convert everything to xland. That's kind of cool that it works, but in this case I would just say, hey, x is equal to y squared, and so this integral is just pi y squared dy. Y squared all squared dy, because x equals y squared, and therefore x squared is y to the 4th. And so if you work this out, you should get 32 pi over 5 units cubed, cubic units. Again, I leave that to you, but there's nothing complicated about this particular integral. Okay. What about if you took the same region and revolved it around the x-axis? Oops. Didn't leave much room there, did I? Well, I don't think we can call this a crown now. I don't know what to call it. It's a cylinder with this sort of bowl hollowed out of it. But it's definitely, the outside looks like a cylinder. The inside is a bowl. So it's a completely different solid. It should have a completely different volume. And we would use the shell method now, because now the strip is the same, the thin bit is perpendicular. And indeed, if you drew one little shell, it's going to look something like this. So that's what you get when you take that strip and revolve it around, this time the x-axis. So, again, integrals from 0 to 2, switch x and y, 2 pi y x dy. X is equal to y squared. So you replace it, and that integral works out to be 8 pi cubic units. All right. So that's variation 1. Does anyone have any questions about it? Areas down to the y-axis. You see how to adapt the two basic formulas to this case. I hope you can see it in two ways. One, just by switching x and y, and two, by actually drawing the strip and revolving it around the appropriate axis and seeing whether you get a shell or a disk and what the volume of that entity is. So I'm not saying you should memorize these two formulas. If you do, there's going to be too many formulas for all the variations. Instead, learn the basic two formulas and how to get them, and then adapt them. Know how to adapt them. That's how I'm trying to advocate solving these problems. So before I move on to variation 2, any questions? I know it seems like I'm not doing too many examples, but actually the whole trick is to write down the right formula. And then the form of the function is normally not so important. You just have to plug it in, and then, yeah, you have to do the integral. But it's getting to that integral in the first place that's the tricky part, or the new part at least. Okay, well, let's move on to variation 2. So variation 2 is the volume, or the area that you're looking at, the region, lies between two curves. Wish I had a little more space here, but I'll deal. No, I won't deal. I need to stack two graphs on top of each other. So please bear with me for a few seconds. Well, I might as well tell you what I'm going to do. If the region you're looking for lies between two curves, how would you find its area? Forget the volume. How do you even find the area? Well, one way you can do it is to take the area all the way down to the x-axis of the top curve and subtract away the area down to the x-axis of the bottom curve. So, I don't know, suppose that the top curve is a little wiggly like this and the bottom curve is just like this. And that's, here's the one. Here's A and B. So if we wanted that area, we could just find this area and take away the bottom area. And you get this area. I'm going to advocate doing the same thing with volumes. If you revolve this around the axis, say the x-axis, you'll get, again, a weird ring. There'll be this interior surface which actually is wider on the outsides. And then the outside of the ring itself will have this sort of, I don't know, it'll have this wavy shape all the way around. Still, you can think of it as being the outside of this solid, no hole, just revolved. So that's like a dowel with a funky edge. And subtract away the inner part, which is sort of, I don't know, it's that funky cylinder there. I don't know what to call these things. There's something that looks like that. I don't really know. Anyway, so basically I'm thinking of this is the hole. This is actually the hole that's taken out of this to give the final solid. Okay, so actually to find this volume, we're going to find this volume, which we already know, or we know in principle how to find, and subtract away this volume, which we also know in principle how to find. Now, lest you think it only works for disks, I will show you that it works for shells as well. I'm going to have to, each picture is going to be a little wider, of course. If you try the same trick for the shells, this time the revolved thing looks like this. So it's sort of floating above the axis. Again, it's some sort of ring, but this time the top has this mottled thing, whereas the bottom is just concave up, like that. Now, that is the same as if you went all the way down to the axis. so that the bottom this time, it still has a hole, but this time the bottom is flat. And I take away this sort of shape. Again, the bottom is flat. It's a flat washer, but now the top has got this concave up sort of nature. So, unlike in the first picture where I carved out the core, in this case I'm sort of ignoring the bottom contour of it, and I'm just carving that out later. So I'm sort of chopping off the bottom. But in both cases, you see, you reduce the problem to saying, find two different volumes and just take the difference. So, volume of two curves, or volume if areas between two curves take the difference between upper curves volume, upper curves revolved volume, and lower curve revolved volume. So find them separately. If you get a negative answer, that's bad. Volumes aren't negative. You probably took the smaller volume and subtracted the larger volume. So you probably just need to switch the volumes around. But maybe not. Maybe you made an actual, mistake in the integration in that case. So just check your work. Never get a negative volume, okay? Not in this course anyway. Mind you, if you could work out a way of making a negative volume of food, you could probably make a fortune selling pills or food or whatever it was. You just lose weight by eating negative volume. No stampede out of the classroom to make money. Okay, in any case. Right, now, by the way, I have seen quite frequently the way to do this problem described as take a strip, say, let's look at this method, and the strip looks like this, say. And when you revolve it, it looks like a washer. It's like a cylinder, but it's got a hole in it. And you can add up the washers and get the final volume. But I just don't see why you'd want to. It's just more tricky. It's a new method, the washer method. You can use it if you like. But I prefer to just use the standard disk method, find the volumes, and then take the difference. Instead of doing it, the washer method, what that does is you carve it up into strips first and take the difference at the strip level. Whereas what I'm doing is take the difference at the volume level. And to me, it's a little simpler. You don't have to remember any other formulas. You just have to know this principle. Now, given that, here's an example. Suppose I take the curves y equals x to the fourth and y equals 2x cubed. Maybe I'll use a different color. How's the blue look on the camera at least? Good. Okay, there is some area in between. And what I'd like to do first is revolve this area about the x-axis. So what will we get? Well, you will get a very thin funnel. The outside is blue. And it gets a little, it's thin at the point there. It's like it just tapers to a point, gets a little bit thicker, and then gets thinner again. So it's a sort of a funnel, like a flower bouquet or just the paper wrapping, a cone type thing. Okay, so How are we going to find the volume? Well, first of all, I haven't drawn any intersection points. This is clearly 0. But we're going to have to solve to find this coordinate, at least the x-coordinate, although the y-coordinate wouldn't hurt. So we need to solve, when does 2x cubed equal x to the 4th? 2x cubed equals x to the 4th. X is 0. Or if it's not 0, we can divide by x cubed, and you just get x equals 2. So this is the point 2, comma, 2 to the 4th is 16. So I didn't really draw this to scale. I didn't draw it to scale at all. 2, comma, 16. I think I did. There's more to scale in the book, if I recall. We're working in 29.1.5 here, by the way, for reference. All right, so now we know something. Which one is the top curve? Well, it depends where you are. Here, the white curve is on top of the blue curve. Here, the blue curve is on top of the white curve. Actually, here's where we care about. So the blue curve is on top, and I'm going to call it y1. I'll keep it in blue. I'm going to call it y1, and I'm going to call the other one y2, because if they're both called y, I'm going to get mighty confused. Okay, y1 is the curve on top here. y1 on top, and y2 on the bottom. Okay, so I'm just going to ignore y2 for the moment. Just take the blue curve, bang, forget all the other junk, take a blue strip, use the disk method because the top of the strip is parallel to the axis of revolution. The disk's going to look like this. The height is y, thickness dx. It's just the standard disk formula. So volume 1 is the integral pi y1 squared dx, and we're going to go from 0 to 2. And so this is just the integral from 0 to 2. Pull a pi out at the first opportunity. y1 is 2x cubed. Sorry, 2x cubed. That's y1. And now you have to square that dx. Whereas volume 2, I'm just going to take, again, I'll use the same method, of course. Same formula. Pi y2 squared dx. And in this case, y2 is x to the 4th. So that's the bit we have to chop out, because it's below. So the actual volume is v1 minus v2, and if you really want to get snazzy, you can combine them into the same integral. 2x cubed all squared minus x to the 4th squared dx. And it's a very straightforward integral to do. I believe that the answer works out to be 1024 pi over 63 cubic units. All right. So don't, in my opinion, don't try to use washers. Just find two separate volumes and take the difference of the bigger minus the smaller. If you didn't know which one was V1 and which one was V2, which one was on the top and which one was on the bottom, and you switch them around, of course, you're going to get minus that answer, which, again, is unacceptable. Volumes have to be positive. Any questions about that? Well, suppose that you would like to find the same region, but I want the volume when it's now revolved around the y-axis. So now the plot thickens. We've got the white curve on the bottom. We've got the blue curve on the top. And now I want to revolve it around the y-axis. So now you're going to get a bowl where this time the blue surface is actually the inner surface of the bowl. And the white surface is the outer surface. And the bowl is thinner at the bottom. It's actually sort of, I mean, it is flat, but it tapers down to a point. And also the rim is thin. It has some thickness in the middle. So that's what we're dealing with here. Now, the thing is, there's actually two legitimate ways we could do this. Let's do the sort of standard thing that we might think of, and that is continue to think of the blue curve as being y1, which was 2x cubed, as on top of the white curve, y2 equals x to the fourth. And I want you to think of this as the shell method. Suppose that the strip looks like this, and the other strip looks like this. So that we're actually revolving this piece around. Well, we can clearly do this with a big blue shell minus the white shell. Or if you prefer, we can take the blue bowl, but with all this junk. So the solid blue bowl. Not just the bowl, but the cylindrical plinth that it sits in and everything in between. And subtract out the white bowl, which is almost as big. And you'll be left with your sort of skin of the bowl, the actual bowl. So let's use shells, and we're going to set it up exactly the same way. Except this time, the v1 is equal to the integral from 0 to 2 of 2 pi x y dx, which now I'm going to put y1, because that's the top one. So it's 2 pi x times 2x cubed dx. And v2, same formula, shells, two pi x. Oh, it's 0 to 2 as before. I should have marked that in on the diagram. X to the fourth. That's y2. And of course, the actual volume I want is the difference. And again, I could combine them into the same integral, pull out the 2 pi, and you get x outside of 2x cubed minus x outside of x to the fourth. Again, you write this as 2x to the fourth minus x to the fifth. Do the integral, and what do you get? Again, I leave it to you. Very straightforward in this case. You should get 64 pi over 15 units cubed. Cube units. Okay. So that's one way to do that problem. Think of this bowl, thin bowl, as the bowl on a plinth minus the slightly smaller bowl on the same plinth, or with stuff around it. But there is another way. And the other way involves using variation 1 in conjunction with variation 2. I'd like to show you how to do that. Hopefully we'll get the same answer, because it's the same volume. We're still revolving this thing around the y-axis to get that bowl-like thing. Let's see what it looks like. I need my blue. So the top curve is, again, y1 is 2x cubed. The bottom curve is y2 equals x to the fourth. And we've revolved them to get bowls. Now, let's suppose instead we took our strips to be horizontal. So what do I mean by that? Well, I take this strip and I take away this strip. And so actually what I'm revolving is this piece here. So what does that correspond to? Well, if I just did the white one, I would now get a solid bowl. It's not, forget the plinth with this cylindrical thing that the bowl's sitting in. This is the real deal. This is the bowl full of milk and cornflakes, okay, or solid. Full of ice. And I take a slightly smaller bowl, which is the blue one, and I'm going to take that away. And I'll still get the same solid, right? Completely different construction from the shell method. In the shell method, nothing in the bowls was filled in. Instead, I had this outer sort of wrapper plinth, I've been calling it. It's like a holder for the bowl. And the bowl itself is empty. Here the bowl is full, and there's nothing outside it. I'm taking away the other bowl. So one thing you might be very interested to know is that the bigger piece is now the white thing instead of the blue thing. So actually, I'm going to use variation 1 because this, in each case, the strip, we're revolving around here. Variation 1 with the disk method. The strip is now, the area I'm considering is down to the y-axis, or at least my strip is. And the thin bit of the strip is parallel to the axis. So, I'm going to use variation 1 and 2. And so, if I were to work out V1, it's going to be the disk method. Pi y squared dx becomes pi x squared dy, because we're switching x and y. But what is x, and where is the integral from? Well, let's just call it x1. And instead of calling them y1 and y2, get rid of the subscript, and instead call them x1 and x2. That's x2. This looks a bit confusing. x1 to the 4th power, x2 cubed. Why is this now x1? Because from the point of view of the y-axis, the white curve is on top of the blue curve, right? Tip your head up. Make your y-axis the x-axis. Okay, I can't do it. That's why I'm a mathematician, not a gymnast. But nevertheless, if that's my x-axis now, the white curve is on top of the blue curve from that point of view. Whereas from this point of view, the blue is on top of the y. Right? I'm taking the bigger bowl, which is the white bowl, and subtracting out the blue bowl. So they're switched around. Again, you can test it out, and you will see that if you get them the wrong way around, you get a negative answer. So, with that in mind, x1 is actually equal to y to the 1/4. And x2 is equal to y over 2 to the 1/3. That's how I want to think of it. Since I'm using variation 1, I really want, instead of y as f of x, I want x as f of y. I want x as a function of y, and I have two different functions of y. And now you can clearly see that the white one is on top of the blue one. So in any case, oh, and I didn't say where the integral went from. This was from 0 to 2. This integral has to go from 0 to 16. Remember, the intersection point was 2, 16. And we're integrating with respect to y, so we need points on the y-axis. So we need pi integral from 0 to 16. x1 is y to the 1/4 all squared dy. And volume number 2, similarly, is the integral from 0 to 16 pi x2 all squared dy, which works out to be pi, the integral of y over 2 to the 2/3 dy. So the actual volume we want is the difference, which, of course, you can also combine into one integral. And it will work out to be y to the 1/2 minus y to the 2/3 over 2 to the 2/3 dy. And if I haven't made a mistake, this needs to equal the same as it did before, 64 pi over 15 cubic units. So please verify that that's the case. We solved the same problem in two different ways. Of course, you wouldn't do it in two different ways unless you were specifically asked to. There's no need to be silly about it. It's enough work to just do it in one way. But if you are going to do it two ways, even just as an example, you might as well check that you get the same answer in both cases. Yeah, question down there, and then I'll come up there.
I don't know if you know this, but generally on the test, do they ask you to do it a specific way, like a shell method or a disk method? Or do they just ask you to do it one way? Because I think it would be easier to do that way if they just ask you to do whichever way you want.
Right, so the question is, do they ask you to use a particular method on the test? Now, in Math 104, I have to say, I haven't really seen it very often. I can't remember too many examples where they would say, use the shell method, but it's not inconceivable, and particularly if you're at another school. Yes, maybe they will say, use the shell method, in which case that would mean you need to use the first method that we did to solve this problem. Because if you take your strips horizontally, you've got disks, right? But remember my principle about the thin bit of the strip either being parallel or perpendicular. So if they say use the shell method, you've got to take your strip so that the thin bit is perpendicular to whatever the axis is. So that will tell you which way to cut it up and help you do it using the principle in reverse. All right, so then there was a question at the back, which was the same question. Okay. So basically, you have to be prepared to do it both ways. Most of the time, you have the choice of how to do it. And honestly, most of the time, it's a no-brainer. This is an example where it's not as clear-cut. Right? Most of the time, there's one logical way to do it, but not always. Now, the only other thing I want to say about variation 2 before moving on to variation 3, see, this takes a while, all these different variations, but we're coming to the end of it. The only other thing is, sometimes you might get a situation which looks something like this. You have some curve, y equals f of x, and you have just a line, say y equals a, and you would like to revolve this area about the x-axis. Now, variation 3, which I'm going to talk about in just a few seconds, is where the axis itself is not the x-axis, but is parallel to it, or parallel to the y-axis. But this is not that. This is not that. The axis is the x-axis. So how do I handle this? Well, this is just variation 2, with y1 is f of x, and y2 is just a. So the bottom volume, in particular, y1, well, let's say it goes around the x-axis. v1 is just, in this case, pi y1 squared dx, and you just copy in whatever that f of x is, all squared. And v2 is pi y2 squared dx. Actually, I shouldn't call it a. That's dumb. Let's call it h. The reason I don't want to call it a is because this was a and this was b, and I can't get my a's and b's and h's mixed up. So this, the second integral becomes the integral from a to b, and y2 is just the constant h. And of course, h being a constant means you can pull it out and get pi h squared, and the integral will work out to be b minus a. But you don't need to learn that. You just need to remember the idea that if the bottom thing is a line, treat that as as the bottom curve. It's not a curve, it's a line, but a line is a curve. So it is a curve. Anyway, that middle bit that we've just chopped out is actually a cylinder. Whatever the big thing is, that we've just bored out a cylinder, and the cylinder has height b minus a and radius h. So of course it has volume pi h squared b minus a. So it makes sense. Anyway, that's just the comment. Variation 2 also includes the case where the bottom is indeed just a line. Tells you how to find areas down to things which are not the axis in particular. And the same would be true if you had a vertical picture where one of the curves was really a vertical line, x equals something. That would be variation 1 plus 2. Okay, but I need to talk about variation 3, and I need to do it pretty quickly because I still need to talk about arc lengths and surface areas. And that's going to take some time too. All right, so variation 3. Axis is parallel to x or y axis. So the situation I'd like to consider is where, again, we have y equals h, and again we have some curve like this, from a to b, And again, we only go down to the line y equals h, but this time, instead of revolving around the x-axis so that there's actually a hole, I'm going to revolve around this line y equals h. So what I will get is a solid. Again, it's like a lump. It's a dowel. It's got a flat circle top and bottom, but curvy outside. All right, how am I going to handle this? Well, two ways of thinking of it. One way, take the strip. The width is dx. The position is still x, which would be relevant only for shells. Doesn't really matter for the disk method, which is what we need here. And now the height is y minus h. After all, this is y, whereas this is h. So the leftover height is the entire height y minus h. What if this line happened to be below the x-axis? Still works, because h would then be negative, and y minus h is actually y plus something. It's y plus minus h, and minus h is positive. So it still works. It doesn't matter whether this is above or below the axis. So, of course, the disk that you get after you revolve this has volume pi, radius is y minus h all squared, or is y minus h, so pi r squared, and then you get dx. So that's going to be the volume there. But what if it was shells? Well, if it's shells, things are a little bit different. I could still think of this as the area going down to the y-axis. So I could actually, or rather than the x-axis, I could do my previous method and make it work, as in use variation 2. Or I could just do the same thing. But you see, that's not variation 3 anymore, really, is it? Because instead of going around the... Well, variation 3 says I'm not using an axis. I'm using something parallel to one of the coordinate axes. So let me talk about the shell method in a slightly different context. And here it is. Sorry about that. That was a little bit incoherent. Let's try again. The shell analogy goes something like this. So I have some other point, x equals h, which is now a vertical line, and I want to revolve this region around that. That's better. So I take a strip, and here's my x, and here's my y, but actually I'm revolving around this axis here, and so what's relevant is that the radius of the strip is actually not x anymore, but is x minus h. Now, wait a second. Here, h is negative. Shouldn't this be bigger? It is. H negative means x minus h is actually bigger than x. So again, it doesn't matter if this vertical line was, say, sitting here or here or here, anywhere. You will still get x minus h. So now, the volume is the integral, and we're going to use shells, 2 pi, the radius, instead of x, we have x minus h, and instead of y, well, we still have the height y. So I'm sort of going a little bit quickly here, but if you compare to what we did before, the only difference is, in the first case, the height y is now y minus h, and in the second case, the radius x is now x minus h. So guess what? All you have to do is replace y by y minus h, if the axis is parallel to the x-axis, or x by x minus h, if the axis is parallel to the x-axis. So if you revolve about y equals h, replace y by y minus h. If instead you revolve about x equals h, replace x by x minus h. And again, this is justifiable even if you don't want to make the revised strips. what you could do is a translation of the coordinate axis. Just replace y by y minus h, and it shoves the whole picture actually down to the x-axis. I'm not going to go into the details of that. The same thing here. If you replace x by x minus h, it just shoves the whole thing over and reduces it to the previous case. So this rule of thumb is legitimate, but again, I think you should try to draw the strips and see what's happening. What is the radius? All that sort of stuff. Now, there is one important exception to what I've just said, and that is this. I should have really written or h minus x if necessary. And similarly up here, or h minus y if necessary. When might this be necessary? Well, suppose, for example, in this case, the axis is actually to the right of the figure. Suppose this is h. And I want to take a strip and revolve it so I get a shell. Well, now the height is still y, but it would be a lie to call this length x minus h. After all, this distance here is x, and this distance is h. H is actually bigger than x. So this now is h minus x. And there's a similar case in the other case when the area happens to be above the curve, then you need to replace y by h minus y. So just do a reality check. Again, a hallmark of this, failing to do this, is that you get a negative volume. You won't get a negative volume in the disk method because you're squaring it anyway. Right? Look at that above formula. The top formula there, v equals integral pi y minus h all squared. Doesn't matter if you write y minus h or h minus y, the square takes care of it. But in the second formula, clearly you're going to get the wrong answer. Should have written a to b here. If you meant, or if you need to have h minus x. So just beware if the axis is to the right of the picture or above the picture, that instead of subtracting h, you instead write h minus x or y as appropriate. So it's getting a little bit hairy. I think we need one last sort of example, a grand example, to several different versions of it to make things a little more concrete. Any questions as I'm erasing the board? Okay. So for my grand example, I'm going to take a relatively simple function. Everything from now on is going to involve the function y equals x cubed and I'm interested in going between 1, x equals 1, and x equals 2. Of course, the height's here. 2 cubed is 8, 1 cubed is 1. And I actually want to take the line y equals 1. And so I'm looking at the area between y equals x cubed, the line y equals 1, and the line x equals 2. And so that's a particular region there. Okay, so I'm going to consider several different questions. The first question is, what happens if you revolve about y equals 1? Well, that's a pure variation 3, right? The axis is parallel to the x-axis. If I draw a typical strip, got a mass exodus from the classroom. I'm going to do arc lengths and surface areas very soon in any case. So let's see what happens here. The height of this strip is y minus 1 because y is all the way down to the axis and I'm taking away 1. And the thickness is dx. The strip is parallel, the top of the strip, the thin bit, is parallel to the axis of revolution. And so I'm going to use the disk method. So it's disks with y replaced by y minus 1. The volume is the integral from 1 to 2 pi y squared, except instead of y squared, it's y minus 1 all squared dx. Again, you can see this by taking the disk. The disk has radius y minus 1 and thickness dx. And so that completely justifies that formula, even if you don't like the translation trick. And so in this particular case, you have to find this integral, x cubed minus 1, since y is equal to x cubed. And you just expand this out and integrate term by term. And I leave it to you to hopefully verify that you get 163 pi over 14 cubic units. All right. So that's a fairly straightforward case. What if we want to revolve the same region? It's gotten a little bit messy now. Suppose we want to revolve it about x equals 2. By the way, the first case we get some sort of, again, it's like a cone, but it's filled in. It's like a funnel, filled in whirlpool or something. But about x equals 2, you're going to get a much thinner sort of trumpet-like shape filled in, witch's hat again. So about x equals 2, well, now, here's my same strip. If I now revolve this about x equals 2, I get a shell. The height of the shell is y, but it's not actually all the way down. See, it only goes down to 1. So I kind of need to think of this region as the difference between this top curve and the bottom curve. So I'm going to have to use variation 2 plus variation 3, where the top curve is y1 equals x cubed, and the bottom curve is y2 is just 1, the height of 1. Another way of seeing this is, as I say, this is y minus 1 as the height of the shell. And the radius of the shell, well, what is this? This distance here is 2, because x equals 2, whereas this distance is x. And so the radius of the shell equals 2 minus x. Again, variation 3 says replace x by x minus 2, except 2 minus x in this case is necessary. So anyway, the volume is going to be the integral from 1 to 2 again of 2 pi, okay, instead of the x, I've got to place 2 minus x, and I'll take the upper curve first, y1, and I'll subtract the bottom curve. I'll just put them both here, 2 pi, 2 minus x, y2. And you might notice we could factor this all out to be y1 minus y2 anyway. So let's do that. It's 2 pi, integral 2 minus x. The top curve is y equals x cubed, and the bottom curve is 1. So this is y minus 1, and that agrees with the cylindrical shell formula, with the radius replaced by 2 minus x and the height replaced by y minus 1. Gets a little complicated. But nevertheless, that's kind of what you've got to do if you want to do this. You've got to think of this as the difference between, well, either draw the shell itself and then write down this formula directly, or think of it as the difference between the top curve, x cubed, the bottom curve, 1, and the shells about x equals 2. So x gets replaced by 2 minus x in the standard formula. Two methods come out the same way. And this, what does this lead out? I believe this is 8 pi over 5 cubic units. Well, I have time for one more example using the same picture, which has now gotten sufficiently messy that I think I should redraw it. 1, 2, 8. What I'd like to do is revolve this about x equals minus 3, which is all the way over here. I didn't even leave myself enough room to see what it looks like. It's going to be pretty hollow. Well, I love drawing on this part. Come in and wonder what on earth was this? Because you see, you don't have the context of this after it's erased. Anyway, so I would like to know this volume. There's the axis, x equals minus 3. So how do we find it? Well, suppose we use strips that look like this. Bang. This is, again, a variation 2 plus 3 deal, because the top curve, y1 is x cubed. The bottom curve, y2 is 1. So instead of x as the radius is now x plus 3. So you're going to actually get a very similar sort of thing to the previous problem, right? I mean, it should be, there's not much difference. Instead of x equals 2, we're just going around x equals minus 3 and using shells. Actually, you know what? I didn't mean to do that method that way, that previous problem. I meant to do that using disks. No wonder you all looked so confused. Actually, you didn't look confused. I'm just imagining it, but hell. Okay, let's finish this one. I'll go back to the other one. Just take a few seconds to do it. To do this one, it's going to be exactly the same as what we just did, but instead of 2 minus x, it's going to be x plus 3. After all, the radius is x plus 3. We're revolving around minus 3, so it's x minus minus 3. So it's going to be x plus 3 outside of x cubed minus 1 dx. And this one is 259 pi over 10. I did that pretty quickly because I've actually already done it for this example. Right? It's just the same, except that instead of 2 minus x, we have x plus 3. So I don't think I want to spend much more time on it. What I really wanted to do is go back to this example and do it the way that I first said, or do it the way that I really wanted to say first, which is by using variation 1. Sorry for this. This is an example where you can do it two ways. So I've got to get through this quickly so I have enough time to do the other two topics, which luckily aren't too long. Well, I'll do what I can. Look, let's go back to the problem where you had to go around x equals 2. I did it an unnatural way. Here it is, 1, 2. What I really wanted to do for this is take strips that are like this, horizontal strips, and revolve them to get disks. So I want to chop this up to disks. And if you do this, then each disk, well, this again is 2 minus x. That's the radius of the disk, right? That's 2, and that's x, so the difference is 2 minus x. And the thickness is dy. And we're going from 1 to 8. So that volume, variation 1 says switch x and y, so it's got to be pi x squared dy, but instead of the x, the radius is 2 minus x. So it should be pi 2 minus x squared dy, going from 1 to 8 on the y-axis, from 1 to 8. So in particular, you'll have the integral 2 minus x. What is x? Y equals x cubed. So x is y to the 1/3. And again, you should get 8 pi over 5. So this is an alternative way and an easier way of doing what I did by shells on the previous blackboard. And that is the way I should have showed you first. So sorry about that. And now the only other thing I want to say, unless there are questions after this, is I want to go back to the example where we were just, the one we just did, where we take the same region and we revolve around x equals minus 3, which hopefully I've left myself room to do now. Okay, we did this just before by taking shells. And there we decided it was variation 2 and variation 3. It was variation 2 because we were going from this top curve down to this bottom curve. And it was variation 3 because we have an axis that is not the y-axis but is parallel to it. What if instead we took strips like this? Well, now it's variation 1, 2, and 3. All three variations, right? It's variation 1 because the strips are now sideways. It's variation 2 because we've got to go between this top curve, which is x1 equals 2, and this bottom curve, which we should really write x2 is the cube root of y to the 1/3. And it's variation 3 because instead of our disks being around the y-axis, it's actually around the line x equals minus 3. So I don't have much time to go into the details, but if you wanted to use this method, first of all, the integral is from 1 to 8 because it's with respect to y. The top curve, well, it's going to be the disk method again, and it's going to be pi x squared dy, but instead of x, we need 2 minus x. No. No, 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 no. No. The distance to this axis here is x plus 3. Right? The axis is x equals minus 3. So it's got to be x1 plus 3 all squared dy. And then we have to subtract the second curve. I keep writing infinity. x2 plus 3 all squared dy. So it's variation 1, pi x squared dy. Variation 3 says replace x by x plus 3. And variation 2 says do it for both the top curve, which is this vertical line, which is now horizontal when I tilt my head, and the bottom curve is y to the 1/3. So you will get this integral here. We can combine them all and get x1 is just 2, so 2 plus 3 all squared, minus y to the 1/3 plus 3 all squared dy. And if you work that out, you'd better get 259 over pi. 259 pi over 10 cubic units. So I've had to rush through that a little bit. There is a much more complete description of how to get that, I hope, in the book. But I have very little time to cover the other two topics. So unless there are any questions, I need to move on. I'm sorry to be in a rush, but 2 hours is not quite enough for all this stuff. Next week's going to be even worse. Okay, well, luckily the other two topics are pretty small, or pretty easy, especially in context of what we've just done. Let's talk about arc lengths. Okay, so without too many details, the idea is we have a piece of curve like this, and we want to know how long it is. What do I mean? Well, I take my endpoints A and B. I take a piece of string, I lay it out over there perfectly, and then I chop it at here, and then I stretch it out and measure it. How long is that? Pretty practical sort of problem. Could come up if you want to know how much metal to build a curved bridge or something. So how would you work this out? Well, without getting into the nitty-gritty of it again, I'd like to show you the prototype of how this is done. Suppose that, well, first of all, the basic idea is to chop it up into many little different segments here. And again, add them all up, add up all the lengths, and let the partition get smaller and smaller, so we're having more and more little approximating segments. So we've gotten rid of a curve and replaced it by a sort of jagged line. So let's look at one of the pieces. Suppose it connects from x to x plus dx. On the y-axis, this is going to go from y to y plus dy. So how long is this curve? How long is the curve? Well, I don't know. How long is the line? Let's work that out. This would be dx. This would be dy. So if you use Pythagoras' theorem, this would be the square root of dx all squared plus dy all squared. So our prototypical formula for the whole arc length comes from integrating or adding up all these pieces. So the arc length L should be equal to the integral of all this stuff. Unfortunately, I don't even know what that means. What is this integral with respect to? What are the bounds? It looks like there's x and y. Who knows what it is? So it turns out that this is the prototype, but there are some nice variations which all follow from that prototype. The standard case looks like this. So here's an actual formula. Suppose you're going from A to B. 1 plus dy dx all squared, square root of this quantity, dx. And just, this is something you just have to memorize. That's the formula, the standard formula for arc length. Just to see how this reduces to the prototype, this is not a proof, just a sort of feeble justification. If you drag the dx inside the square root, it becomes dx all squared. And you think of this as dx all squared, which is that, and dy dx times dx, maybe the chain rule can tell us that that's actually dy. Again, it's no proof at all, but nevertheless is some sort of justification. So that's the standard formula for arc length that you just have to learn. And it has a few variations. And, actually you can use variation 1 if you like. And if you did that without going into the gory details again, if you happen to know, see, this time the curve is the same. There's no area underneath it, so you don't need to worry about which way it is. But if you happen to know, instead of y in terms of x, you might also know x in terms of y. And so in that case, you might want to write dx dy and integrate with respect to y. And then you just have to make sure on this picture that you go from capital A to capital B. That's actually not going to work unless the function is monotone. So I'm going to cheat and draw it like this and say that the other one is valid. Luckily, though, there's no variation 2 because you can't take the arc length between two curves. And there's no variation 3 because there's no axis. This is not a revolution sort of thing. So basically, these are the only two formulas. And this one comes up once in a blue moon. So that's the formula. However, we like to make things more interesting or difficult and give you one more formula. Remember parametric coordinates, where x and y are both in terms of t? There's a parametric form as well. It looks like this. The length is the integral of dx dt all squared plus dy dt all squared dt. And that is taken from the first parameter t0 to the last parameter t1. Again, imagine if you pull the dt into the square root. You get dt squared, and that would knock out these denominators and reduce you to this prototypical formula. So it's another special case of that formula. Now, my suggestion is that you more or less remember these three formulas, especially this one and this one. You might never, ever need to use the bottom one. So the reason I say the topic is pretty short is because there aren't really any variations other than those formulas. So, however, the integrals can get a little bit interesting because they involve square roots. They can often involve trig substitutions, but they can also involve some tricks. So I'd like to show you an example or two of arc lengths. You must remember the formula, though. No one is going to give it to you on the final or the midterm, not in Math 104 anyway. Here's an example. Suppose you take y and x in parametric form. X is equal to 3t squared minus 12t plus 4, and y is equal to 8 root 2 t to the 3 halves. Yuck. And t is a parameter that goes from 3 to 5. Okay, every t you plug in between 3 and 5 will give you a pair of coordinates x and y. And you do this for every t between 3 and 5 and plot the points you get, and you'll get some curve. Could even intersect itself, unlike a regular function. What is the length of the curve? I'm not even going to try drawing it. Actually doesn't intersect itself, I don't think, because the y coordinates are increasing. But in any case, what is the length of this? Well, let's use the formula that I just wrote up. The arc length is the integral dx dt all squared plus dy dt all squared dt. And that's going to go from 3 to 5, because that is where the range of t is, the domain of t is. Okay, so what is this? We have to differentiate dx, well, we have to differentiate x, we get 6t minus 12. But we have to square that. How about dy dt? Well, you've got this constant 8 root 2, and then the 3 halves comes down, and you'll get t to the 1 half. You have to square that. The derivative all squared. So what is this? Well, you get 36t squared. 2 times 6 is 12, times 12 is 144. T plus 12 squared is 144. Plus, well, 8 over 2 is 4. 4 squared is 16, times root 2 squared is 2. So you get 16 times 2 is 32. And then there's another 9. 32 times 9, 288. And that's what you get. So if you work this out, you get 36t squared plus 144t plus 144 dt. And you might notice that the original was 36t squared minus 144t plus 144. Because of this magic number 288, that's changed the minus to a plus. So you can actually factor this directly, that was kind of lucky, into 36, well, let's write it this way, into 6t plus 12 all squared. That was kind of lucky, wasn't it? And because this quantity, 6t plus 12, is positive, you can just take the square root. And I'm going to leave that to you. What's the answer? Well, the answer is all the way over here. 72. Okay, so most of the time these integrals are really, really nasty. If you're really lucky, then you get a perfect square, and this is a common trick. This is a common trick that somehow the bit that you add on just magically completes the square for you and everything works out nicely. It's not really a completing the square because in this case it takes care of the t piece rather than the constant piece. But still, just be alert for that trick. In the book I look at a much harder example in regular coordinates as opposed to parametric, namely y equals log x, and the integral you get is a nasty trig substitution. So that's a bit of a challenge. Now, I don't even have time for questions right now. I will take some at the end after the video has run, has stopped rather, but I have 10 minutes to deal with surface areas. Luckily, it's almost the same as arc lengths. Almost the same. There's a prototypical formula and a few different formulas, a couple of variations on, but nothing too nasty. So let's just take the last 10 minutes. Minus however long it takes me to erase this. All right. So again, I start off with some curve. This time what I want to do is I do have an axis, unlike the arc length case. Say it's the x-axis. And I revolve it, but instead of getting a solid, I want you to just imagine getting the surface, the shell. So I'm not filling it in. There's no sense in whether the area goes down to the x-axis or the y-axis. There is no area. It's just a curve. So I get a shell rather than a solid. It's a surface. Not a shell in the sense of cylindrical shell, but I get some sort of hollow, just a surface. What is the area of that surface? If I had to paint it, how much paint would I need? Well, I'm going to do the same thing that I did before, take a little approximating region, and again, it's going to be between x and x plus dx. So it's going to have dimensions dx and dy as shown, and again, I have this length as root dx squared plus dy squared. But now I'm going to revolve this and approximate it. So what do I actually get? Well, I get what's called a frustum of a cone. It's like a cone with the top chopped off. Now there's a nasty formula for the volume of a frustum of a cone, but it turns out that, again, I'm going to pull out a bit of an approximation. Let's just suppose that we take the same length and just sort of flatten it out. It actually doesn't matter too much. We can imagine that instead of this, it's just a strip that looks like this. It has height y, and it has length dx squared plus dy, all squared. Again, that's not the same as this, but when the strips are very, very thin, this and this have very similar surface areas. So this can unfold, if you cut it out and stretch it out, into a big rectangle. Well, it'll be a vertical big rectangle like this. Long, long strip. That side is just that square root, whereas this side becomes 2 pi y. The circumference of this is this dimension here. And so we get the formula for the surface area, A. But again, it's just a prototype formula. It's very similar to the arc length formula, but you need an extra 2 pi y times the arc length piece. And again, I don't know where it goes from. So just by the same sort of trick or transformation, again, this is not a proof. I'm just going to tell you what the formula is. If you just go from A to B, I haven't even drawn that, you get almost the same formula. 2 pi y, 1 plus dy dx, all squared dx. So it's the same formula as the arc length formula, but with an extra 2 pi y. With an extra 2 pi y. And that is to take into account the fact that you're taking that bit of arc length and you're revolving it around a distance of y. And when you revolve it, it becomes the radius, area swept out is basically the circumference, 2 pi y. Okay, so that's the standard formula. And again, it has to be memorized. And the good news is that you can take your arc length formulas, any of them. The other one is fine, you know, dx, dy, or the parametric one. And you stick a 2 pi y out the front, and it gives you the surface area formula. Okay? So that's good. That's good, and most of the examples can be done in a similar way. For example, if we took this one over here, then you'd have the same formula, but you'd have a 2 pi y out the front. And you would just replace y by 8 root 2 t to the 3 halves. And you'd get the same integral at the end, except that there'd be an extra factor of t to the 3 halves and a constant. So you could solve that problem as well. So the surface area problems are pretty similar. So I could write down all the variations, or I could refer you to section 29.4, which has them written out. There is one thing that I need to say, and there are examples there as well, and I don't have time to give any, I'm afraid, but there is one other thing. There are a couple of variations here that could appear. You might take your little bit of curve and revolve around the y-axis instead, and this time you get the outside of this sort of bell here. It's like a clarinet bell. What's the formula got to be then? Well, the piece of length is still root dx squared plus dy squared, but now the circumference that you're moving it around is based on a radius of x. So you need a 2 pi x factor instead of 2 pi y if the curve is revolved about the y-axis. So it's sort of a switch x and y, but it's really just take the arc length formula and stick in the 2 pi x instead of the 2 pi y. So that's sort of variation 1 in a way. There really isn't variation 2, though, because you can't have the surface area between two curves. There's no area to start with. So there's no variation 2. There could be a variation 3, though, I'm afraid. What if you took your little bit of arc length and the thing you want to revolve around to get your surface is y equals h? Well, then, instead of 2 pi y, that has got to be 2 pi y minus h. Same sort of thing, right? The distance from this bit of curve down to the axis is y minus h instead of y. And similarly, variation 1 plus 3, if it was about a vertical line, x equals h, you would put 2 pi x minus h. I have to say, in Math 104, I have very rarely seen any deviation from that standard formula for surface area. All right, there's still a couple of minutes, well, maybe 2. Is there any question? I've done a lot. I've bombarded you with formulas, variations. I apologize. I had a lot to do, but one question maybe for the video. If not, we'll stop the video. Anything? Yes? So for the surface area, y here is in terms of x. Okay. Now, of course, you could take that same formula. If x was in terms of y, then you would simply replace dy dx and this dx by dx dy and dy, and make sure you change the bounds, but you still need that y out the front. Unless, of course, it's about the x-axis. So you can, what I'm trying to say is take any of those 3 arc length formulas independently and stick the right factor out the front. 2 pi y for the x-axis, 2 pi x, or for the y-axis, or one of the variation 3 things with an x minus h. But that's independent of the arc length piece. So it doesn't matter what the axis is. You can use any one of the 3 arc length formulas with the appropriate factor inserted. So draw a picture if you're not sure. Okay, next week, something completely different. Improper integrals. Improper integrals.